Hey everyone, today I want to talk a little bit about gears. So, the goal of each of these problems that I'm about to do is going to be to find omega b, or TB, in terms of omega A and TA to make conclusions about gears. So we're going to have a bunch of different gear setups, and we're going to talk about each of them. We're going to start very simple, with just two gears here, A and B. A is going to have some rotational speed, omega A, and we want to find omega B. So naturally, we can figure out the direction of omega B, which is shown here, because just intuitively we know that these gears are going to interlock. This is going to push this way, which in turn is going to rotate gear B this way. Another way that we can describe this system is that because these gears are locked in place, if I were to label a tangential velocity VA at this point where these two gears are locked together, this is going to be equal to VB. So these linear velocities are equal to each other. However, due to the difference in radius, this means we're going to get different angular speeds. So let's go ahead and write out that VA equals VB. We can substitute in for VA, omega A times R, and for VB, we go ahead and just substitute in omega B times 1/2 R. Our R's cancel, and we just move the 1/2 to the other side, so omega B equals 2 omega A. So nifty, when we go from a larger gear to a smaller gear, we get an increase in angular speed. There's our first conclusion. Let's look at this other simple problem where we have our bigger gear A has a force Fa on it. We can determine the direction of the torque by using the right hand rule and see that it will act in the page, which I have indicated with an X. Now, if we look at the point of contact, then we can see that gear A is going to push onto gear B with this same force, Fa. Assuming that you're not losing any energy in friction, right, then these forces will be equal to each other. However, once again, the radii between these two gears are different, which is going to generate our difference in torque. So, let's go ahead and define what TA would be. That is the cross product between R and Fa, which ultimately simplifies to, and we'll say in the negative direction, because it's pointing into the page, negative R Fa. Let's make that subscript a little clearer. Alright. TB is going to be Fa cross 1/2 R. Let's go ahead and use the right hand rule in order to determine the direction of this torque. So if we have our distance 1/2 R pointing to the left, go ahead and just try out the right hand rule, and we're going to see that our TB would point out of the page, which I've indicated with a dot. It's like an arrow, right? There's like the end of your arrow, the back of your arrow, and then this is the front of your arrow, so the arrow is pointing at you. So clearly, we have the torques acting in opposite directions. So that's important to note. Now then, we're going to solve for FA in terms of TA and then substitute that in. So, FA is negative TA over R. Substitute that in to, and let's just simplify this real quick. This just goes into F1/2 FAR, which is positive. And so we get that TB equals negative 1/2 times TA over R times R. R's cancel, leaving us with negative 1/2 TA. Again, let's note that the difference in sign here indicates that TB is going to point in the opposite direction of TA. So, we've lost torque when we go from a larger gear to a smaller gear. Let's go ahead and move on to a more complicated system, and we're going to see what we can conclude about this. Let's think about each of these steps individually at first. So for this rotation, we have, we're going to go through this pretty quickly this time, as opposed to explaining everything out. So, I'm going to go omega A times R, 1/2 R times, and I'll call this omega 1, and then I'll call this one omega 2. So omega 1. So omega 1 equals 2 omega A. Omega 1 times 1/2 R equals omega 2 times R. And again, all of these equations we're just getting by setting the linear velocities equal to each other. And so we can note that this 1/2 omega 1 just equals omega A again, right? So we're noticing that even though we put this intermediate gear in between these two gears of the same size, their angular velocities are still the same as each other. Omega 2 times R equals omega B times 1/3 R. Get that omega B equals 3 times omega 2. Right, and then we'll go ahead and see what omega 2 is in terms of omega A. So omega 2 is 1/2 of omega 1. And omega 1 is 2 times omega A. So omega 2 is just omega A, right? So you get 3 times omega A. All right. Now the key here was to demonstrate that we could go through all these steps, lots of steps, or we just look at the first gear in the chain and the last gear in the chain. If we're not losing energies across these gears, then we can say go down here that the VA is still going to be equal to VB, or at least the magnitudes of those velocities are going to be equal to each other. The directions change, right? But the magnitudes. So we get omega A times R just equals omega B times 1/3 R. And we get that omega B equals 3R, or 3, whoops, omega A. Right? And this shouldn't be surprising. This shouldn't be surprising at all, but it's good to check. Now, we should expect a similar effect with all of these torques. So if we look at this system of gears, we have this force acting here that then is going to push this gear up, which is then going to push this gear down, and it's going to push this gear up again. Right, and assuming we're not losing any energy, then all these forces are going to stay the same. And in real practice, you know, you lose energy between each of the gears. But if this force at the end is the same, all we have to do is solve for the force, substitute that back in, and find the torque on the final gear, right? So if we do torque A equals RF, F equals TA over R, and then from there we know that TB, which by using the right hand rule we're able to deduce that it points into the page. So TB equals 1/3 R times F. And we just said F is TA over R. So TB equals 1/3 R times TA over R, which is simply 1/3 TA. And again, direction-wise, this is in the opposite direction of the TA. Right, and so over a series of gears, we can simply jump from the first gear to the final gear. So now let's go ahead and look at a system with compound gears, right? And so what a compound gear is basically just a gear stacked on top of another gear on the same pivot. So this little gear that's stacked on top of gear A is going to have an angular speed omega A, right? And so we're going to solve for VA prime and VA at first to see what the effect of this is, right? And this is very easy. VA is just omega A times R. VA prime is omega A times 1/2 R. Right, and we see that when we just shrunk that radius, we were effectively scaling the linear speed down. So now, at this point of contact, the VB that we're going to be using is the VA prime, right, because they're locked together. So now the linear speeds are locked. So if we have VA prime equals VB, now we can say that VA prime, which is 1/2 omega A times R, this is going to equal 2R times omega B. And we end up getting that omega B is 1/4 omega A. So compound gears are very useful for scaling speeds down or up, depending on what you're trying to do. So in our final example, we have a compound gear with a torque that's pointing out of the page. And again, we want to find the torque on B. So we can write that whatever linear force that this gear has on it, this gear connected to it also has, right? So it's just simply the radius that is changing, which is going to result in a change in torque. So TA equals R times F, and T on the little a equals 1/2 R times F, right? And so we scaled the torque down. And from here, we can solve for F, and we get that F equals 2TA over R. Right, that's another way that we can write this force that's going to be acting on B. And this is going to push into B like this. So this is F equals 2TA over R. Right, and so the torque on B equals 2TA over R times 2R. Which is ultimately going to equal 4TA. So we've significantly increased the torque produced from gear B, right? If we just used a single gear on this, then we would get twice the torque. But by adding this compound gear, we got 4 times the torque. So that's a very powerful effect. So with that, we've demonstrated a lot of different mechanical advantages that gears can bring. So, thanks for watching.